gonna call the R&D department, I suppose. And
I'm Astha. I'm working as a senior DevRel advocate at Algorand Foundation. And we'll be giving a session on advanced cryptography in AVM. So yeah, thank you for having us. In this presentation, you'll be getting insights into some of the exciting applications that you can build on Algorand. So over here, like what we would want is that you guys will get like some insights into AVM, specifically in the cryptographic way, on how we are able to achieve what we have in the AVM. But not just in the AVM perspective, we'll also have a greater understanding of the Algorand as a whole, so that basically when we use AVM, how are we able to get innovation and security in the Algorand. And you guys would be wondering that, okay, in 25 minutes, how will we get to know such core concepts? Yeah, I mean, we have actually, we wanted to respect your time, as well as we wanted to give as many concepts as possible. So that's why we have a 25-minute abridged version specifically for Decipher. And probably in the future, we would be making a 1 hour long session for this as well. So we'll be starting with understanding the developer skill funnel, and we'll be going from left to right. And this is basically to understand how we are supporting the blockchain developers in upskilling themselves. So we first go into the blockchain fundamentals, which are basically the core concepts that we have. In this, how we help is that we have many mentorship programs, we have academies like UNDP, and then what we do is that we help developers in understanding SDKs, nodes, and signing. This is where developers start getting their hands dirty in terms of like understanding which all tools we have, and we do this by conducting workshops at universities, going to conferences, interacting with different developers. And then there is a third stage, which is basically smart contracts. This is where the developers start understanding what all capabilities in terms of blockchains we have, and how we can build different applications on top of it. And for this, we have different boot camps. I think Joe Polney has done a fabulous job in terms of TypeScript boot camps, and Chris and Evert in terms of Python boot camps. Also, this is the fourth skill that we would want people to become aware of, which is cryptography. We currently do not have that much content around it, but based on the interest that we get, we would definitely love more and more people to get to know about what all primitives we are using, the opcodes that we are using, how will it benefit us. And I hope this presentation also gives a little bit insight into this. Now coming to what we as Algorand want to achieve. So the first thing that we would wish to achieve is having a more upward mobility within Planet Algorand for developers. So more and more developers coming to our platform, understanding our platform. And we also would want to have community catch up. So as we all know, there is a lot going on in terms of opcodes. There are different applications, different changes in protocol that are coming up. So we want that everyone comes together and we don't like leave anyone behind. So we definitely want everyone to catch up on the latest trends that are there. The third is basically we do have a lot of applications that are built on Algorand, but we also want even wider range of applications. From, for example, supply chain, like in terms of finance, there are like endless possibilities that we would want to achieve. And this also would result in having heavy utilization of the chain in terms of more number of transactions, more number of smart contracts, and also there are few opcodes which are little heavier, so we would have an increased fee as well. And remember, cool attracts cool. So we would like have, if we have like cool projects coming up, we'll also attract many game changers, many innovators, and many like really good projects coming to our ecosystem as well.
Right. So let's. just an overview, first of all. So in terms of smart contracts, there are typically talk about two types, logic SIGs and applications. And the difference being that applications are meant to store state and have access to storage in terms of, for example, boxes. And as a result of that, they have higher, sorry, next. Yeah, so because logic SIGs don't actually go into storage, we can trust them to do more in a time, like, yeah, we give them more time. Wait, slow down. So for applications, we only allow 700 ops, you can call it, like kind of like gas per transactions, whereas for logic SIGs, we allow much more. And there's a trick that allows us to combine these two types of smart contracts to basically make full utilization of all the opcodes that we have. And there's a really cool thing that you can do with logic SIGs, which is that you can call them with a so-called unfunded or uninitialized address. So that's an address that has never, it's just like a public key that's been generated, but it actually hasn't been funded yet on chain. And I'm not sure like if I've heard that much about this being used in other chains, because this allows for some, let's call them relay-less protocols, where on other chains they might require a third party or like this whoever's running the protocol to jump in and call the smart contract on behalf of a new user. Whereas on Algorand, someone could just kind of post the logic SIG and the smart contracts, and then they can kind of take a step back, and then users can themselves, even though they don't have any algos yet, they can call logic SIG and in a group transaction, and as long as by the end of that group transaction it has been funded, it's fine. And so, yeah, these are some of the things I'll be going through, and there's also an extra part at the end. Let's move on. Basic. So first we have these kind of standard hash functions, and I'll mention some other ones later as well. But next one. They allow for something, for example, commitment. So let's say you want to run a rock paper scissors game on the blockchain. You can use a hash function for that. You can commit to a move, and then you can blind it with like a random value, and then you can, once both players have committed, they can then reveal their things. Then you can use it for simple random output. So it's very useful for example, next step, with Fiat metric, where you're trying to turn an interactive protocol into a non-interactive one. Next up. Then there's compression, where typically you might want to have you might have a lot of data that you want to compress to like a 32-byte or 64-byte commitment. For example, if you want to put it in a box title, you can use it for that. And then we have these Merkle trees, which are like used everywhere in blockchain and allows you to do this commit to a large number of values, very, very large, and then only store this root of the tree, and then very efficiently open up like a path through that tree to show that you committed to a value. So moving on. Then we have these, I call them basic signature scheme. They're basic in the sense that they're all kind of like packaged for you. So we have ED25519 verify, and it allows you to do, to verify normal signatures. It's worth noting that Algorand itself, our transactions, are based around the ED25519 signature scheme. But we also have ECDSA verify, and it comes in two flavors. The top one here, SECP256K1, is used by Bitcoin and Ethereum. So I'll come to it later, but if you go to the next one, we can use these for interoperability purposes, account abstraction, identity, so on. And I have an example, actually. We have, what's next? We have Janus, the founder, over there. So they were using this to allow people to use their Bitcoin or Ethereum wallets to take that key material and use it to create abstracted account on Algorand by putting these opcodes in a logic SIG. So that's an example for the application. When we have these incentivization opcodes, I don't know if I guess they're left here, but previously we had a talk by Transaction Labs or NFTs. So using these opcodes, you can, as we're transitioning to incentivized nodes, you can create these so-called Reti staking pools. So you're locking up your algos, and then getting yield on that, and in return for helping out with the consensus. And because you have locked up algos that are now earning yield, well, you can then mint tokens off of that. So you can do liquid staking basically, and use those tokens for something else. So this is the Reti chess opening. And yeah, transactional, that's their logo. And then we have the VRF. So the VRF basically it's the core of Algorand and the pure proof of stake consensus mechanism. And it was invented by Silvio. And we have this 20, 2,990, 1,500 rule. It's a mouthful. But basically at each round, you have 20 blocks that are proposed. And then you have a committee, which is called the soft vote committee, which it's a committee of 2,990. They come and they pick out of these 20 blocks, which one is the block that has the lowest hash output. And also they will also verify that it was done correctly with the VRF. No worries. And then after that we have the certification vote, so this committee then goes ahead and checks, is the block that the previous committee proposed as the most valid one, is it actually valid? Does it have any double spending? Does it have any other illegal stuff, right? And if that's the case, then the block is added to the top of the block height. The key thing here is that there's no one person actually coordinating this whole process. Everyone is self-selecting themselves to propose the block or to give a vote, right? And this means that the adversaries don't know before it's too late. So in the same breath that the person is announcing their status, they're also announcing their preference or like their suggestion, right? Whatever their vote or block. And also the fact that we only look at 20 potential blocks is incredibly valuable. So of course we're like propagating all the transactions so that they're on everyone's mempools and these things. But we only look at 20 blocks. We only have for each round only 20 blocks being propagated. And so and this scales, right? So it's fixed even as stake and the number of entities grow. And so that means that it's just incredibly efficient. And that's why we say that we have solved the blockchain dilemma because of these things. It's secure and it scales really well. And then I put it here because people, whenever I talk about this, people are always like, oh, okay, what's the catch? And so I just added there. I don't think it's a huge trade-off, but we have this idea of being online. So the stakers have to register themselves as online, and then we expect them to be online and have this liveliness to them. Go back. So I like to compare this a little bit. So this is like when the Pope dies. These are the cardinals. They arrive or they meet up. They meet up they go to the Sistine Chapel, and they vote. They discuss and they vote for a pope. And the key thing here is that they don't really announce to anyone like what's going on. It's not really public. They just release smoke, either black or white. And when it's a white smoke, it means that there's a block. So similarly, Algorand is similar in that sense. That the blockchain just says, oh, this is the next block. And unlike the Catholic Church, no forks, right? So no schisms. This is an anti-pope. So Benedict XIII, he was born in Aragon, not too far from here. But no forks on our end. And this is comparable, if you can contrast it with, for example, with Bitcoin or Nakamoto consensus, they have this idea of, well, it's whichever longest chain or which one has the most difficulty that wins. And so, you think that your transaction is in a block, the node tells you, hey, yeah, I found a proof of work. And that is fully valid. Well, no, someone comes, nope, my chain is longer, and so it disappears, right?
I want to know what the prompt you use for that photo.
Yeah, it's chains and ogres and Mad Max and yeah. Next one, please. So we had this VRF verify opcode, which basically the same code that's being used for Algorand for the PPOS stuff. We're exposing it as an opcode. And so we have this randomness beacon that was developed by Applied Blockchain, and now we brought it in-house. Use it. You can use it for. You can use the VRF verify for PPOS protocols. So you can do Sybil resistant stuff and Oracle stuff. But there's a really cool thing I would love to see, which is using it for games. And there are certain casino games that have so-called no hidden state. So that's where there's a dealer. They just take a card and then just put it face up. So like blackjack or baccarat. There's no hidden state. There's no like poker plays with hands in there, kind of keep a secret. And so you could run these kind of games with the VRF. And there's going to be a talk by Giorgio on randomness and how you can take the VRF and then kind of get like a bounded output. So you're checking, sampling from 1 to 52, like the number of cards in a deck. Here is some example. Companies building on Algorand. So we have Gora, who are using this for Oracle network, and we have Cupstakes World. I don't see these are seen, but he's around here somewhere. they did a lottery using VRFs. So moving on, then we come to easy math. Just a quick note on privacy. So here's a check.
Could you go back a couple of slides? One more. A curiosity. No, maybe. Are we going to talk about the church? No, a curiosity. Do you think that there is a inherent limit on how many online addresses could participate? Like, supposing a super extreme, like one microalgo.
Yes, so that is a challenge, right? And that especially now with node incentivization, where we want to make sure that people we're basically checking like are addresses actually online or are they just claimed to be online? And if they are online, there's a certain probability that they would have contributed in some way with a vote or these things. And if you just allow anyone, that's why we introduced this 30K minimum now, because we're incentivizing this, and so there's money involved, right? If you allowed, like even with one microalgo, you would, because this is stored in memory, this calculation, to make it performant, it would just this attack where you just have like, bajillion mini algo, microalgo accounts. I guess the minimum algo is already required, like, a minimum algo just to be
one algo,
okay, one algo, you have a lot of,
address.
Yeah, then it would, there's a problem because it would increase our hardware requirements. So that's why now we're requiring for incentivization minimum 30K.
Because the calculation of the total online stake couldn't be achievable with the current requirement.
It wouldn't be feasible without also increasing minimum node requirements and hurting decentralization in that way. But luckily we do have pooling with this stuff. Yeah, but it's good. And in the paper which you are a co-author on, actually, Michele, we talk about this, like these attacks, why we have a minimum.
The real number was.
Yeah, I don't have it in my head now. Or it's a good question. So here's a check from 1975, where maybe $25 was a lot. I don't know. So it's from the president, Gerard Ford, and he's sending money to this church. And you can see a bunch of information here, right? You can see the signature, you can see the amount, date, these things. And so we're talking about privacy. This is kind of like what a normal transaction looks like on a blockchain. You have a sender, receiver, amounts, right? And then if you move on, when we talk about anonymity, this is what we're talking about. We're hiding, typically, definitely the receiver is being hidden, but also, you can also, the sender is also kind of, anonymized, especially if you keep going to it like several times. And then we have confidentiality. Here we're hiding the amount, so you can see who's sending to what, but you don't know how much is being sent. And then when you combine these two, you get what we call full privacy. So I just want to make that clear because it's not really, sometimes people talk about privacy, but they only mean one of these things. Wait, go back. And I just want to mention one thing here. I didn't cover the dollars, but in Algorand we do have ASAs, and so you could even have what's called like multi-asset shielded accounts and these things where you hide not just who is trading what and how much, but also which currency are they using. Are they using algo and these things? So, but moving on, so we have these we call the easy math opcodes, and we have these, and crucially, we have this pairing check here, which is only available for these so-called pairing-friendly curves. So BN254 and BLS12381. So we have these opcodes for those two curves, and they allow like incredibly powerful things. So you could use these for ring signatures, BLS signatures, BBS signatures, and also the KZG commitment scheme, right? And just to give a comparison, because there's a bunch of signatures there, right? Signature schemes. So with normal one like this, you have one secret key, one person signing one message, and they have one public key that the signature can be checked against, right? And the application is like, everything we've been talking about, right? Standard stuff. Then we come to ring signatures. Here you have one person signing one message, but they're including a bunch of other people's public keys and obfuscating themselves with it. So you can't really tell which one of these public keys belongs to the signer, like who's actually signing. You just know that there's like a cloud of them. And this allows you to do anonymity. Of course, I use payments as an example, but it doesn't have to be anonymous payments. It could be voting, these things, like for games, for example, if you're blackballing someone, these kind of things. And you want to do it on-chain. Then we have BLS signatures. And typically there you have for these multi-party applications. So you have many people, many secret keys. They're signing one message, but what you can do is you can aggregate their signatures and their public keys into one. So you actually only do one verification tick. That's the same cost, even if there are many or few. And so you can do this for multi-sigs, but also so there's something called like threshold T out of N signature schemes, and this is like simpler to implement than alternatives. Then you have the BBS signatures, and this is still it's like a draft being developed right now, and this is really cool. Like this is related to identity and what's called selective disclosure, and we talk about self-sovereign identity, right? With this, what you have is you actually have three parties. You have an issuer, approver, and a verifier. So what you could do, let's say I'm approver. My name is Jared. I am so old. I'm from Sweden. I have all these attributes about myself. I can, I code them as individual messages, and then I go to an issuer, so let's say a bank or the government or whatever, and they give one signature, right? They sign it once, all of these attributes about me. And after that, I never interact with them again. And then what I can do is, go back there. So,
Okay, sorry.
and then what I can do is, obviously I could just show that signature, but that would be dumb. What I can do instead is I can create a proof of knowledge off of that signature. And then when I then, if you have like a bouncer, right, who's checking how old are you, I can just show a proof of knowledge of that signature that has been signed by a public key that is trusted, right, by a trusted issuer. And I can do this called selective disclosure, where I actually only reveal my age. I don't have to reveal my name or anything like that. And what's really cool is also I can do this repeatedly. So I can repeatedly prove that I'm over 18, but all of the signatures or all the proof of knowledge that you get out of this are unlinkable. So even if they wanted to use this information about me, they can't really link it with anything else. And so I think this is a really, really powerful application called BBS signatures, still working on a draft, but it could be verified using pairing check. So, and another thing about pairing check is you have these KZG polynomial commitment scheme. It's a mouthful. It allows you to commit to a polynomial, set of polynomials, and then evaluate that without actually revealing that much about those polynomials themselves, or the details of the points. This is very powerful, and it's used for something called Merkle trees. So these are basically Merkle trees, but even stronger. Like they're vector commitments, but you're basically encoding them as like a polynomial going through the points, and it's just more efficient than even Merkle trees, which are already very efficient, right? And I know on other chains they're talking about switching over. For example, Ethereum, they have like this for their accounts. They're talking about switching over from Merkle trees to Merkle trees, and so I think we're going to hear more about those. Then we have ZK Snark, which are like the ultimate stuff. So there are two types, two big ones that use pairing. So it's a Groth 16. It's a paper by Jens Groth from 2016, and then there's something called Plonk, and I'm not even going to try to pronounce the acronym for that. But moving forward, so with this we can do full privacy, interoperability, like ZK bridges. You can do even more gaming stuff, even more identity stuff. And there are some applications I suggest you look up into them. I don't think we have time to go through them now, but these are like seen on other chains. I would love to see them on Algorand. ZK regex, ZK email, ZK passport, right? And so before we had this guy named Julio. I was hoping he would show up, but I think he's somewhere else. He had his own talk, right?
Yeah, he had a talk.
He had a talk. So before Julio, this is a guy in the community, right? Before him, we knew that we had with opcode budget and everything that we could verify Groth 16 style ZK Snarks. But then, because Devrel proved it actually way back. But then when he came along, he said, no, I can also do a Plonk, which are like, without going too much into details, they're better for various aspects. So I would recommend that you go check out his GitHub, julioP/algoplonk, or just Google algoplonk. And we're going to hear more about that, actually. So I've said a lot of good things about these, but then there's a key drawback with these things, which is called the trusted setup. So when you're defining a ZK circuit, basically you define circuits, and there's something called like a pre-processing step where you process that circuit and it produces some values, and included is something called toxic waste. And the idea is that you have to this is like an artifact of KZG, is that whoever does that, they have to throw away the toxic waste. So they have to like delete it from the computer. If not, they can use it to create fake proofs. And I'll go. And so trusted setup, what they've done to deal with this is they've created these MPC processes, so multi-party computation, where you have like hundreds of people contributing some random entropy. And as long as one person is honest and deletes this stuff from their computers, then it's safe, right?
Is it only one that needs to delete it?
It's enough for one person to be honest and delete, because you're kind of adding all the randomness, and as long as but yeah, it's not enough time to go through all that. So what about the future, right? So if you ignore the pairing parts, well, I would love to see like these, if you add like 825519 for these opcodes. And there's also like restretro, which is kind of a wrap around this, and so because then what we could do, like even cheaper ring signatures, simpler cross-chain atomic swaps, on-chain HD wallet, public key derivation is a mouthful, but I don't know. We introduced or we announced HD wallets, and with if you had easy add and also if you added also an HMAC function, you could basically verify that one address is the child of another address, or that these two addresses are sibling addresses on chain, which you can do. Then there's also this other type of ZK called inner product argument ZK, and it's not as efficient as the other ZK snark examples I gave, but there's no trusted setup, and so there's that big advantage. And there's something called bulletproof which use these, and Monero have these. Solana introduced them now for their confidential transactions stuff. So maybe something that we could explore if we added this opcode and these opcodes. And then the extra part is lattices. So first of all, this is you. I like to say this is an elliptic curve, and all of your public keys are points on this curve, or a curve like this. Moving forward, actually it's more like this because it's integers and the x and y are bounded, and so it looks more like this. So if we rewind a little bit, I mentioned that Algorand has these self-selecting committees. So for each block, we are subsampling a small part, right, of the Algorand stake, and we're using them to make decisions, right? And and everyone who's running a node, they know that everything is being done properly because they're also running their own nodes, so they can trust them. But the question is, how can we convince others that these blocks actually been properly created, right? So you could provide a proof that has been signed by a supermajority of stakes, so not just a subsample, but actually, a big chunk of them. And because this will take too long to do for each block, we can do instead a commitment using a Merkle tree of the block headers for the last 256 rounds to attest. So you basically create a proof every 256 rounds. And we can use something called compact certificates, which there's a paper out there, you can check out, which allows us to efficiently store and then validate these kinds of things, like that this amount of people have signed, representing this amount of stake, has signed this type of statement. And this is the basis for our state proofs, right? And so now state proofs are being produced all the time by mainnet, and yeah. And so there's a question asked by the people at Technologies, which is led by Chris Pikert, who's an expert in cryptography. Can we do something else other than ECC, elliptic cryptography? And the answer is yes. So they decided to do instead use lattices. So this is, for people, I showed you a curve, elliptic curve. This is a lattice, and so basically you have these two vectors, these kind of like arrows, and you can combine, you can add them together, and then the combination of them spans like these points, right? So that's a lattice. And here, this is a specific example called the closest vector problem, where you're trying to go back a combination of these two to find the closest point on the lattice that's closest to this red dot. So for you, and the reason why we want to do it is because of this, right? The quantum computing stuff, which is going to break elliptic cryptography. Move forward. So we have this another AI-generated Falcon. It's called Falcon with extra feet.
This is very good prompt engineering.
Yes. So we have these two opcodes that are used for state proofs. So Falcon to verify Falcon keys. So that's a lattice-based signature scheme, and that's post-quantum secure. And then we also have another type of hash function called sumhash, which we're using to create these Merkle trees. They're currently in what's called vFuture, or they're not actually a mainnet, but they're kind of ready. Like in case there is someone who wants to use them, they're kind of ready to be added to the next, the next version as usable opcodes. And what you could do with these, so this Falcon itself, you can put in an LSIG, and you can maintain a post-quantum secure address. So, even though consensus, i.e. the VRF, is still vulnerable to post-quantum security, post-quantum attacks, and quantum adversaries, at some point we're going to switch, right? But if you don't want to wait until then, you can use Falcon Verify in an LSIG, and you can maintain your address up and indefinitely. There's this one thing though, that the LSIG, the encoding of the LSIG, cannot be a valid ED25519 point, because then it can be spoofed, like signatures can be spoofed. If you go next, then of course you can verify state proofs. The idea is that you could verify state proofs in the AVM from other AVM chains. So you can create interoperability between them. And for example, if you have your own idea of an AVM chain, you can create a bridge for it. And you can also do something like incentivize testnet, because testnet is also an AVM chain. So instead of manually, like if you have your users, your customers playing around on testnet and then getting testnet tokens for it, and then manually, sending them stuff on mainnet, they could just bridge their testnet tokens for mainnet tokens. In a very, that's also an example you could do. Now, conclusion.
As we wrap up our discussion, we can just look back to all the advanced cryptographic opcodes that we looked into. So first one is verifiable random functions, which basically gives us how we can provide like Algorand's unique consensus mechanism. Then we looked into EC math, which basically opened doors to ZK applications. And then we also looked into how we can use lattice-based opcodes in future, which will allow for interoperability. So definitely would like to say that more and more people should actually check out these advanced features. And if, for example, you're interested, definitely you should attend our boot camps, our hackathons. They are intensive and would definitely learn a lot about it. And we are here to support you. So Yared is here, the whole Algorand is over here. So in case of anything that you want to discuss with us, you have any queries, please reach out to us. And the AVM's advanced capabilities will help us to position Algorand for continued innovation. So thank you so much.